questions today. I mean, the most important is to understand the physics, the fundamental physics law.
Some of your knowledge is we have studied in the high school, but long time no revise.
You have studied electricity and magnetism during at high school.
Some part of it, yes.
Oh, some part. Okay, good. But yeah, so please. Something like this. So y, z, okay. This is the plan x, y. Okay, this is the freewheel. Okay, and so the electric field is parallel to xy plane and make an angle of. I think it's like this. Yes, exactly. In the xy plane. Yes. No, I don't think so. No, because I think the angle is written that the angle of 53.1 measure from the x plus x axis toward the x. Yeah, I think it's this one, not this one. Okay? Welcome.
Everything I do, I don't fucking.
Any other questions? Hello? Oh, there is much people. Do you have any questions about what we have seen before? Okay, I have one question for you. Do you need more time? Do you think to study all the chapters 21, 22 until 30? Do you think that 13 hours is enough, or is too short, or do you need more time? In other words, do I go too fast for you?
A little bit faster, not much.
A little bit here, a little bit fast, okay?
Yeah.
Some other opinions?
I think that 30 hours is, I mean, it's in the middle zone. It's not that fast, but the way that people putting one physics lecture every single day in 2 weeks is a little bit intense.
Yes.
So 30 hours is okay, but the frequency of it is intense.
So, what you mean is that doing the fundamental physics 2 in 1 or 2 weeks is too intense, too dense.
Yes.
But 13 hours is equal? It's okay?
Yes.
Do you need more? You do not need more time to. Thank you.
So.
No, it's because it's to adjust the number of hours of this lecture for the next years.
All right.
But unfortunately, I'm coming from France, so I cannot stay in Vietnam
Too long.
for a long time. So we cannot manage this course in, let's say, 1 month or 2 months, okay? So because I'm not living here, so this won't change. I will have to do it in 2 weeks.
All right.
So after this lecture, you will come back to France.
Exactly. Okay, so let's start this because this morning will be quite dense. Okay, so yes. Okay, so yesterday I presented to you the Ampere's law, which is the equivalent of the Gauss law for the magnetism. If you want to go, you can go. Okay. Okay. So let's study an example just to make sure that you have understood everything. So. Can you see? It's okay? Okay. So let's consider a wire. Okay? But this is a section of the wire. Okay? So the wire is carrying a current, and let's say that the current is going to us. Okay? This is, so everywhere there is a current. You understand? Going through us. The total current is I. Okay. So now I have two questions from the center of the section. Okay. What is the magnetic field at the point M, let's say at the distance R, okay? And second question, what is the magnetic field inside the wire? Okay? You have to imagine that the wire have a radius big R, and I would like to know inside to the point M, for example, inside the wire. You understand what I mean? Okay? It's a big wire like this. Okay? So, to do that, we are going to apply the Ampere's law. So, first of all, we are going to consider a closed loop, as I said yesterday, a closed loop going through the point where we want to calculate the magnetic field. Okay? So we are going to consider this closed loop here, passing through M. I don't see if you see it. Yes? Okay. So this is the first loop. And we, of course, we are going to consider a second loop, a closed loop here, passing through M. Okay? So here are two Ampere's loops. Okay, so for the first one, for the loop passing through N, okay? So the first loop, do you see it? So we can apply the E in it. Okay, so this is the general formulation of the Ampere's law. Of course, in this kind of symmetry, the B is always like this, and it is the same in the center. Okay, so the magnetic field, as I said before, is circular. Okay. Okay. So what it implies for the loop passing through M, it is important to quantify the current inside the loop, which is encircled by the loop. Okay? E net. So in that case, okay, the current passing through the loop, inside the loop, is not big I. Okay? But we can assume that it is proportional to the section of the loop passing through N. You understand?
Yes.
So it is something like I time, so P R squared over pi big R squared. Okay? So this is the ratio of the two sections. The section inside and the total section. Okay? Of course, okay, let's say N. Yes. R is only the distance to the point. Okay? So R is here. Sometimes it's here, sometimes. It's okay? R is the distance between the center and N. Yes? Yes or no? No, you are not convinced? Okay? I is the total current, and the current inside, which is encircled inside this inside loop, is the ratio P pi R squared over pi big R squared. Okay? And B here, B ds, is only the B that we are looking for time the total length of the cycle, which is 2 pi r. Okay? So at the end we have mu 0 I R2 of big R2 equals B times 2 pi R. So B at the point N is equal to mu 0 yes, mu 0 I over 2 pi time time R over R2. Okay? So this is for a point inside the section. Is it okay for you? Okay, so now for the loop passing through N. Okay, so now we are considering a point outside the wire. Okay, so now it's more easy. We have already calculated. We can just say that mu 0 E, big I, because now the total current inside which is encircled by the loop is total I equal B of M times 2 pi R. Okay, so B of M is equal to mu 0 I over 2 pi R. So, to conclude, let's draw the density, the magnitude of the electric field as a function of the distance r from the center. So at one time, this is big R. Big R is the radius of the section. Yes? Okay, and so you can see that at the beginning, inside, it's not to learn this, but inside, the magnetic field is proportional to the distance. Okay, so it's going from 0 to somewhere here, which is linear. And for R equal big R, then we have this. Okay, and then after that, the magnetic field decreases as 1 over R, and so it's like this. Okay? This is just an exercise. Don't learn the formula, but just learn the method to retrieve the results. Do you have any question? It's okay for... Yes, please?
Is the loop going through the end at the R, the R is the radius?
No. Yes. In here, small r, it's a distance. Okay, so I use the small r for n and for m also. Okay. Sorry.
Teacher, so here,
Yes.
here's the small n.
No, here it's small. Yes, small r. Okay, it's a distance.
So you use the small r for both radius.
Exactly, for both point n and for m. Okay? The main difference is that for the point n is inside the wire. Okay? So the total current which is uncycled by the loop passing through n is not equal to big I, but just this. Okay? Okay, other question is okay? Okay, so let's go further. So now I will have to present you what is solenoid and toroid. Okay, so let's start by what is a solenoid. So, by definition, it's a wire, so it's a single wire, which is wrapped, let's say wrapped, around a cylinder to form a tight helix. Okay, so let's consider this cylinder. Okay, and a solenoid is you take a wire and you wrap it around it. You see that? Like this. Okay? And then you can run a current in the wire. Okay, so the current, for example, is here. And so now the current is going here from here because it's an helix. You see what I mean? Okay. So of course we can say that this is the length, and do we need the section? No. Okay. Okay, and the section now. Sorry. So this is the section of the current, of the solenoid. Okay. And so now the current, yes, the current is going here. And here it's going like this. Okay? And it's here. Okay, so now the question is inside the solenoid, okay, there is almost uniform magnetic field in that direction. So B is magnetic field. Okay, and outside there are some magnetic field like this a little bit, but outside here, far from the solenoid, the solenoid, B equal is very different. Is very close to zero. Okay, so let's write this. Yes. Okay. Also, I need to introduce a new parameter for a solenoid. A solenoid is characterized. So solenoid is characterized by, of course, the current E, and n, small n, is the number of turns of the wire per unit length. Okay, so for example, if you have a unit length here, okay, so you have to count the number of wires in this unit length. Okay, so n is the number of turns of the wire per unit length. Okay, so now the question again is, what is the magnetic field inside the solenoid? So a solenoid inside a solenoid, there is of course the magnetic field is created by the current I, okay? Okay, so there is a magnetic field created by the current I, and we want to calculate it. How are we going to calculate it? We are going to apply the Ampere's law. So, for example, we are going to take a loop, for example, this one. Okay. So, remember, in magnetism, the Ampere laws, we need to consider a loop which uncycle the current. Okay. So, for example, this loop. So let's say that this one is small l, okay? A loop of small distance l here. Okay? Okay, so now let's say A, B, C, D. Okay, so let's orient AB toward the B and Of course, as I said before, outside the solenoid, we can say that the magnetic field is almost zero. Okay, it's not really exactly almost zero, but very far from the solenoid, it is almost zero. D equals 0. So the displacement B, the magnetic field, is parallel to the displacement AB and perpendicular to BC and AB. So if we apply the Ampere's law, so D mu 0 I net encircled by this loop is equal to the displacement of the magnetic field around a loop. So we can say that it is equal to the displacement about AB plus BC plus CD plus DA. Okay? You understand this notation? Okay, it's the same. So we are going to calculate the displacement B times ds over AB plus BC plus CD plus AD. Okay? So, as I said before, outside, this is 0. Okay? Over BC, sorry, no, this one is 0. But all are 0 except this one. Okay? This one, DA and BC, is because B perpendicular to DS. Okay. This one is because B equals 0, and this one is because B perpendicular to DS. I'm sorry to be, it's okay?
According to what law?
Ampere's. Sorry. Okay? Okay. So again, the displacement of the magnetic field B over BC and DA is equal to 0 because B is perpendicular to DS. And over CD, it's 0 because the magnetic field is equal to 0. So at the end, it remains only this. Okay? So, and now what is the current encircled by this loop? Okay. It's the current time the number of terms per unit length times the length. Okay? And this is equal to B times the length because the length is AB. Okay? So, conclusion, the magnetic field inside the solenoid is mu 0 E times M. Okay? And again, small m is the number of turns of the wire per unit length. Okay?
Teacher, I have a question.
Yes, go ahead,
So-
please.
Okay, so according to the law, because two vectors are perpendicular to each other, so two vectors multiplied by f is equal to 0. So why is equal to BDS, but the CD maybe is here, CD is here. So why CD is equal to 0?
This is this integral of a BC. Okay, it's not BC which is equal to 0. It's the integral of B scalar ds. Okay, but the vector B is perpendicular to the vector ds here.
Yeah.
So the dot product B times ds is equal to 0. Okay? So if you make the sum of 0, it's always 0.
Yeah, I know. But I asked the CD why 0.
CD because outside
Yeah.
outside the solenoid, this is outside, the magnetic field is equal to 0.
So that means it's outside, so it's not
Exactly.
have electric.
Okay? It's okay for everyone? Other questions? No other questions? Okay, great. But okay, so just this is the magnitude of the magnetic field created by the inside fluid. But we have to specify also the direction of the magnetic field, and I'm going to do it here. Remark. So you won't be surprised, but the direction of the magnetic field is indicated by the right hand rule again. So the right hand rule again is you have to wrap the solenoid with your hand, and then you have to the fingers are oriented in the direction of the current, okay, for base 1, for example, and then the thumb indicates the direction of the magnetic field, okay? So remark, the magnetic field is indicated, is oriented according to the right hand rule. Okay? Okay. So now let's see another device, which is not a solenoid but a toroid. So it's in fact here the solenoid is something which is cylinder. So a toroid is a solenoid which is circular. What does it mean? So let me try to draw a little bit this, to draw this. So if I'm trying to okay, so so here are the wires, and inside there is this. Yes, sorry. Sorry. You see what is it? I'm not drawing a, and the current is for example here in this, let's say here. Okay, so here is it in, okay, so this is a solenoid. I'm not drawing it well, but it's a Tor. Okay. So we can see, we can have a view from the up, from the yes. So it's like this, and okay, and so the current, for example, is going here and here. Okay, so like this. Okay. Okay. So the of course the solenoid is also characterized by n, or sorry, the total number of terms is n times 2 pi, let's say big R being the radius here. Okay. R. So this is the total of terms. Okay? Okay, so just to a last application of the Ampere's law. Okay, you have to. So in order to calculate the magnetic field, so inside there will be a magnetic field, as I said before, which is circular now. Okay, so we have something like this. Inside. Okay? So to calculate the magnetic field inside, again we are going to consider here a closed loop. Here, for example. Okay. So this is the Ampere loop. Okay, so you follow me? The loop here is circular. Okay? And so we are going to apply again the Ampere's law. And this. So mu 0 E net. So now E net is the current which is uncycled by the Ampere's loop. So it's always N times E. Okay? It's the total number of terms times E. I, sorry. It's okay? And this is equal, so of course the integration of the displacement B ds. So because the magnetic field is uniform, it's equal to B times 2 pi R. So big R, let's say. Okay, so just B is mu 0 N I over 2 pi R. Okay? Okay, this was a last example. Any question? No? Okay. So now I need absolutely to start the new chapter, the last chapter. What time is it?
8:05.
Okay, I have to finish at 9 something, 9:45.
9:50.
9:50. Okay, great. 15.
T, yeah, T.
19. Wow, okay, so let's go. Okay, so the last chapter is. Sorry, let me check if I have nothing. Okay. Okay. So the last chapter,
Actually, is lay the paper up.
chapter 30, is about induction and inductance.
Teacher, please get
Yes?
get paper up.
Oh, sorry. Sorry. Okay, so just to clarify everything, okay? So far, we have seen that a loop with a current in a magnetic field is submitted to a torque. Remember? Okay, so with a loop or a current, okay, or a wire. Sorry. A wire, not necessarily a loop. A wire with a current placed in a magnetic field is submitted to a force, to a magnetic force. Okay, so this was chapter 28. Okay. Just previously, we have seen also that a wire with a current can, or not can, but creates a magnetic field around it. Okay, and this is chapter 29. Okay, I'm just doing a summary of the. And now we are going to see that a magnetic field, a change in a magnetic field, can create a current. Okay, so we are going to change. We will see. Let's say a magnetic field. Sorry, let's note. Can create a current in a wire. Okay, so this is the reverse phenomenon. Okay, so how was discovered this phenomenon? Okay, it was like this. So this is Faraday. So Faraday was a very famous American physicist. Okay, and so how did he discover this phenomenon? So let's consider a loop. Okay. which is connected to an ammeter. Okay? So there is no current at here, there is no battery, no current. Okay? And then imagine that we can bring close to this loop and around this loop something like this. So this is a magnet, okay? And a magnet has a south pole, of course, and a north pole, of course, okay? And, of course, the magnet is has a natural magnetic field, okay? So, the magnetic field is going like this. Okay? And now, so if everything is fixed, everything is immobile, there is nothing. Okay? But now, imagine that we can move inside the magnet through the loop. Okay? So with a velocity. And in that, sorry. Hello? Hello? I'm sorry. I think there is no more battery. But okay, so I said if you move the magnet inside, toward the loop, then you will have in current here. You will detect a current, and here and here. Okay, so let me describe this. If the magnet is moved, let's say, towards or not, or how to say, yes, toward the loop, we will detect. And so we induce, we call this current, and induce current in the loop. Okay? So if the magnet is moved toward, but it's not, in fact it's not toward, but let's say relative to the loop. So it could be toward the loop or far away the loop, but okay, but it's just a move, it's always a motion, a relative motion, okay? So if the magnet is moved relative to the loop, then we can detect a current inside the loop. So this is, I'm sorry, there is no more battery. So this is the induced current, okay? And this phenomenon is called induction. Okay? Induction. Okay, so now let's quantify a little bit. Okay, to quantify a little bit this phenomenon, we need to introduce the magnetic field flux through the loop. So definition. It's the same definition as the electric field flux. Okay, the magnetic field flux through the loop is, so we noted phi b is the integration of b times dA over all the surface A. Okay? So again, if we have, let's say, here, this is A, and we are going to, or let's say, A, whatever, the loop, sorry. And dA is, like this. Okay, dA is a vector, and B is like this. And A is the total, of course, A is the total surface. Okay, this is a definition that you have already done, or already seen, okay? But instead of the, we have seen this equation, but instead of B, we had E, right? Remember? Electric field, okay? Okay, so, of course, I just mentioned it rapidly. The unit of the flux is Tesla, the unit of the magnetic field, times meter squared. Okay? We also, it's just to mention it, it's also called Weber, which is one of the other physicists which who discovered this phenomenon. Okay, so now we can formulate the Faraday's law. The Faraday law says, oh sorry, there is no more. Hello? It's a last minute. States that in that case, of course, I don't know if there are batteries somewhere. Okay, I will continue like this. Okay, or maybe you can hear me like this. Okay. So the Faraday's law said that when, let's say, yes, that, okay, can I, yes, the induced, so let's say when the flux of B through a loop wire is changing, then it appears and induces EMF, electromotive force. Okay. So the Faraday's law states that when the flux of a B of magnetic field through a loop wire is changing, then it appears an induced EMF, which is, let's say, like this. everyone? Yeah? Of course, just a remark. If the loop is composed of n turns of the wire, okay, then the induced EMF equal minus n time, okay, because now the magnetic field is going through n wires when n turns of the wire, n loops, okay? Okay, just an important remark. The variation of the flux is not necessarily the variation of the magnetic field, okay? Because you can modify the flux of B by different manner, okay? The flux of B can vary. So the magnetic field change, but also when the surface, so the portion of the loop of the area is the portion of the area in the field B changed. Or another way is also to change the angle between the angle between A and B change. Okay, so just remember that the variation of the flux of B does not necessarily mean the variation of B. It could be this, but it could also be the fact that the portion of the area in the field B change, or the orientation of the loop of the area is changing also. Okay? And I will have to finish that now with the lens. So the Lenz's law specifies the direction of the induced current. Okay? So, of course, the induced current, as seen previously, also creates and induce magnetic field. Okay? So, and induce current is important to see that. Also create and induce magnetic field. Let's say BE. And the Lenz's law states that the magnetic field has to be opposed to the change of the magnetic flux. Okay, so I'm going to write this. Lenz's law. Can you read me? It's okay?
Yes.
States that the direction is such that the induced magnetic field, the induced magnetic field opposed to the change in the magnetic flux that created the induced current. So it's a little bit complicated, but read it slowly. The Lenz's law states that the direction of the induced current. So here we have an induced current, and the direction of the induced current is such that the induced magnetic field created by the induced current is opposed to the change of the magnetic flux created. That's great. Okay, let's see for example. So just be careful. The induced magnetic field is not necessarily opposed to the magnetic field that creates the induced current. Okay? Let's see an example. So, for example, if you have a loop, a circular loop like this, okay, and we have to consider the same loop here. Okay, so here we have the magnet, similar magnet. Okay, so of course the magnetic field here is like this. E. Here also. Okay? E. Okay. So now if I move in the magnet in that direction. Okay? So this means that do you hear it? Okay? Okay. If I move the magnet in that direction, that means that I will increase the flux of B. Okay, so here the flux of B will increase, okay, because the magnetic field close to the magnet is more intense. Okay? So what is the direction of the induced current in the loop? If the flux increase here, so the induced current has to oppose the increasing of the flux, so it should open, so it should be in that direction. Because it induced. Okay? In that because in that so if the current is in that direction, okay, then the magnetic field induced by the induced current will be in that direction, and then it opposed to it will decrease the flux. Okay? But here, if you do this motion, okay, so now Phoebe is decreasing, right? Are you okay? If you move the magnet away from the loop, okay? In that case, you decrease, the flux of B will decrease, okay? Because the
intensity of the magnetic field far from the magnet is less intense. So now the current should be in the opposite direction in order to create and induce magnetic field which oppose the flux of B. You understand what I mean? Okay? So be careful, the induced magnetic field is not necessarily opposed to the magnetic field originally. Okay, so just to make a remark, so in fact the Faraday's law said that the change of the flux of B creates and induce electromotive force. So it is like we have this, okay? It's like we have an induced battery in the loop here. Okay? It's just a remark. Okay. Any question? So it's a surprising phenomenon, right? Induction. Okay, but more surprisingly, can I move?
Yes.
Can I move on?
Yes, yes.
Everyone, it's okay? Okay. Where is my page? Okay, so 13. The next part will be more surprising now. Induce electric field. So okay, so let's consider again the same experiment. Okay, so what I want to say is, okay, let me consider again the same experiment. Okay, so again, if you, so here O is the position here, and is the magnet, and S is the magnet. Okay, so if you move the magnet relative to the loop, okay, so you will create, let's say, an induced EMF, and then you will create an induced current, okay? But this induced current is appearing because there are some charge, right? There are some charge in the wire. Of course, a wire is full of charge, okay? But the interesting is, if you remove the wire, okay, remove the loop, so now we have, so here is the position of the loop at the beginning. Okay. experiment, then surprisingly, you will observe an induced electric field. Okay? And the induced electric field will be like this. And this is the induced electric field, which is at the origin of the induced current. Okay? So, in fact, actually, the moving, let's say, the change of magnetic flux through, let's say, and but now the loop is an imaginary loop, okay, because there is no loop. So an imaginary closed loop induces or creates an induced electric field. Okay? And this, which can move the charge to create an induced current in the real loop. Okay? So, I repeat, actually, even if you don't have the loop, a real loop, but imagine a circle here. If you move the magnet, you will change the magnetic flux through this imaginary loop, and then at the place of this imaginary loop, you will create an induced electric field E. Okay? And this electric field can be experienced if you put at this place a charge, then you will observe the rotation of the charge. Okay? You will observe the motion of the charge.
Teacher, may I change the battery?
Oh, sorry, yes, I don't know how to do it. Thanks. Okay. Perfect. Perfect. Thank you very much. Thank you very much. Okay, so having been this idea in hand, we can now reformulate the Faraday's law. Can be reformulated as I'm not going to make the demonstration, but okay. So the how to say? Okay, so the modern way to formulate the Faraday's law is that this displacement, the circulation of the induced electric field time ds is equal to minus the sorry. Yeah, okay, I can just give let's say, it's not a, it's a qualitative demonstration. So, if you put a charge here, imagine that you have a test charge here. Okay? If you put the charge, okay? So you change the flux and you put the charge in that direction. The charge Q. So if we consider a charge Q in the induced electric field. So, of course, the charge will be submitted to the force F. Okay? The work of the charge to make one turn, okay, will be the sum of the induced force time ds equal this. Okay? And because, okay, I will say that the induced field is circular, okay? And so this is equal to Q E induced time 2 pi r, where r is the radius here. Okay? Okay, so this is the work to make one turn. But what we saw, by definition, the induced electromotive force is the work per unit charge. So that means that the induced electromagnetic force is equal to this work divided by Q. So it is equal to 2 pi r, the induced electric field. Okay? And of course, more generally, it's not really a demonstration, okay? Generally, the induced EMF is equal to this, okay? It goes, and this is, so it's equal to Q, yes, Q, I induce this, okay? So it is equal the displacement of the induced electric field. Okay, that's why we have this. It's just a qualitative demonstration. Okay? Okay. Okay, I have you any question? Okay, yes. I would like to make some important remarks. in fact, the induced electric field here has a slight different nature of a natural electric field. Why? Because you can see that, okay, the induced electric field lines are circular loops, right? Induced, it is important to note that induced electric field lines are here closed loop lines, okay? But real, let's say not real, but natural, let's say electric field always goes from positively charged to negatively charged, remember? So, how can we say it? Not in normal, let's say normal electric field, electric field lines go from charge, positive charge to -1. You understand? Okay. So in one case we have normal electric field lines which go from positive to negative, and in the other way you have induced electric field lines which are closed loop. So it's not possible in the second case, in the induced electric field line. So there is no positively charged here. Okay? So that means that it induced electric field line it has a different nature of normal electric. Okay? So this is, let's say here. Sorry. Can I turn my page?
No, please,
Okay.
1 minute.
Do you understand this? Is it important to have this, to keep this in mind?
Teacher.
Yes?
That's in the
The work.
electric field.
The induced electromotive force is the work per unit charge.
Because the table.
Sorry?
The table is.
Can I continue? What?
Okay, you can continue now.
Okay. So what I want to say is that induced electric field it has a slight different nature from normal electric field. okay? Because normal electric field always goes from positively charged to negatively charged. And especially, we can, for an induced electric field, it's not possible to define an induced electric potential, okay? For an induced electric field, it is not possible to define induced potential electric, So this induced electric potential does mean nothing. Okay? Does not mean nothing. There is no meaning of it. No meaning. You understand? You understand what I mean? Because the induced electric field is circular, so we cannot define somewhere a positively potential and a negatively potential. Okay? Okay, so let me finish this chapter by. Do you have any question? It's okay? Okay, let me finish this chapter with inductors and inductance. Just to, in order to have the notion. Okay. So for that, I am going to make a comparison between electricity and magnetism. Okay, so in electricity, you remember that we have defined capacitor. You remember what is it? A capacitor is a device designed to store electric energy. Remember? In magnetism, we are going to define inductor. So I'm going to an inductor. Of course, yes, I also mentioned that a capacitor can create electric field, right? In the similar way, inductor is a device to create magnetic field, okay? And inductor is a device that creates a magnetic field in order to store magnetic energy. Okay? Okay, so generally, an inductor is composed of a wire wound into a coil. Okay? So, generally, a solenoid is the basic inductor. Okay, so the symbol is like this. Okay, so a conductor sorry, not a conductor. Sorry. An inductor is characterized by its inductance. Okay. L is N phi over E. Okay. So where N, so in this equation, so L is the inductance, N is the number of turns of the wire. Is it time already?
No, not yet.
Okay. N is the number of turns of the wire under. I is the current that creates the B. Okay. And of course, phi B is the flux of B through a section of A, through the section of the conductor, the inductor section. Okay? Okay, so in electricity we have capacitors, and the capacitors are I don't remember do you remember the formula for the capacitance of, you have somewhere? It's, sorry, Q over V, but after that for two planes, when you have two plates connected, it's epsilon 0 sigma over D, no, something like this. Sorry? Yeah, you have it? I don't, just to make sure. Do you have it? Yes, exactly. Epsilon 0 A over D. Thank you. Oh, okay, whatever. Epsilon 0, but the definition, sorry, it's Q over V, right? Yes, it's okay. Yes, it's Q over V. Okay, this is the capacitance, and here the inductance is equal to M phi B over I. Okay, and so this is capacitance. And you remember that I said that a capacitor is able to store the electric energy U, okay, UE equal Q2 or over 2C, or if you prefer, CB squared over 2. Okay? This is the stored electric energy in a capacitor. I want make the demonstration, but you can find it in the textbook. The magnetic energy stored in an inductor is simply 1/2 Li2. Okay. Okay, so just to give the unit of L is you can see that is Tesla meter square over ampere, and this is called Henry, and it is node H. Okay, so just to finish.
Wait 1 second. Well,
Sorry, any question? Okay, so can I turn the page?
yes.
So for what is the inductance of a solenoid? Oh, this the end. This is the end. There is no more. So let's say inductance of a solenoid. So again, a solenoid is a typical inductor. Okay. So you have the solenoid like this, and you have the current E, and you have so the length L, let's say, and the section A, okay, and you have N turns. Okay, of a wire, and you have E. Okay, E like this. Okay. So the current induced the magnetic field B. B is equal. I don't know if you remember inside. Okay, B is equal to mu0 En, where n is the number of turn per unit. Okay, so the flux of B through A is equal to BA, right? A being the section of the solenoid. Okay, so but this is this is times n because there is n turns of the wire. Okay? And so this is equal to, so of course n is equal to small n, the length, okay, A, B. Okay? So now we can define the inductance by this. So it's equal to N phi B over E. Okay. I'm sorry. No. Sorry. Yes, this is N phi B. Okay. N phi B is the number of turns, okay, here. So we can see that it is N L A B and divided by E. But now if you replace the B, it's equal to N L A over E times mu0 E N. So at the end you have mu0, the I is not, so you have only Yes, I have something. You have n squared. Oh yes, there is no n. Sorry. Why? I have a L somewhere. Okay, let's see. Yes, I'm sorry, because we have two big L here. Okay, so let's say small L. Small L is the length. Okay, so here it's a small L. Okay, a small L. So we have mu 0 A L times n squared. And what I want to, I'm not, yes, I have to take this, but what is important to note that L does only depend on its geometry. Okay, so it's like just to conclude this part. It's like capacitance. You remember, capacitance only depends on the geometry. Okay? Okay, and to finish the... Oh, sorry. The last part will be 30.5, will be the self-induction phenomenon. Okay. Okay, so what is a self-induction phenomenon? So we have seen that a current creates a magnetic field. Okay. So, if the current which creates the magnetic field is changing, okay, when this current is changing, then the created magnetic field is changing, okay, and then it induces it creates an induced current. You see what I mean? Okay? You have a current, a magnetic field. If the current is changing, then the magnetic field is changing, then there is an induced current. Okay? And this, so a current in a wire is a self-inductance. Okay? So this is self-induction. This is called self-induction. Okay? And what is the inductance of this self-inductor? According to Faraday's law, okay, the induced EMF equal minus n the variation of the flux, but this is also minus the variation of n flux, n phi b, but n phi b is LE, so the induced, this is an important equation, the induced electromagnetic field created by the variation of the current is simply equal to minus L, the variation di over dt. Okay? So this is the current. That creates, this is the current. That creates B. Okay? And this is the electric induced EMF that generates the induced current. Okay? Okay, and just to finish short, so I'm sorry, I was a little bit late. Okay, so if you have this, okay, and okay, so this is a battery. Okay, so and this is the current E. Okay, so if E is increasing, okay, if E is increasing, then the induced electromagnetic field is opposed to this. So you will have this, and this is the induced current. Okay? But if the current is decreasing, for example, then, according to the Lenz law, they will appear in that direction, and then the induced current will look like this. Okay?
Teacher, hold the paper up, please.
Okay?
Yeah, okay, but yeah.
And last thing, so okay, we cannot define an induced potential, okay, but because in a self-inductor it appears induced EMF, okay, around an inductor, we can have the electric potential difference V, let's say VAB, for example, VAB equal CL equals minus VI L. Okay. So this is a self-inductor, and So again, if the current which generates the magnetic field is changing, then it appears an induced electromagnetic electromotive force which generates an induced current. Okay? Okay, so I'm late now, so I will finish this course, and unfortunately it is the last session, so I'm open to any question. Please have your question now or never. I'm kidding. Yes, it's time, I know. Sorry to be late.
If I don't ask you, in USDH we have another lecture.
Yes, question? Do you have any question? No question? Okay, so I would like to thank you very much for your attention. I am very happy to be here among you in Vietnam. It's a great country. You are great students. Okay, so just to finish this, I recommend you, if you have any advice, just to continue to be serious, to write. Okay, the lectures, it's very important for me. Don't forget to write, to try to solve some problem, and you will improve your skills. But do not, please do not stay in front of your screen and just watch the screen, okay? Do not just stay on the screen. Do not just watch the screen or the video. It's not like this that you can learn, and it's not like this that you can improve your skills. To improve your skills, you have to write, to think, and to read. Okay? Write, think, and read. Okay, on this, I'm wishing you all the best for your career and academic careers. Okay? Thank you. Yes? Okay, I will, as you know,